All right, welcome everyone. We've got the top of the hour here. Let's get started on part two of the SANS Cloud Flight Simulator webcast series. I'm Ben Allen. I get the pleasure of taking you through protecting Kubernetes clusters with admission control today. Um, There we go. Quick bit about me. I'm a security architect at SANS Institute. I've been doing a lot of Kubernetes security and observability work over the last year and a bit. I'm also one of the contributing authors for Security 540. And my contact info is on the slide here. Hold a bunch of SANS certs as well. And you can reach out to me on LinkedIn if you like. We've got a lot to cover today, so I'm going to be hanging out in the Cloud Security Discord for about a half hour or so after this webinar, and happy to take questions there. If we've got some time at the end, if things run really, really smoothly, then I'll take some live as well, but focus on Discord for now. What we're going to cover today, real quick in an hour, it's a really fast introduction to Kubernetes in case it's new to you in the space. We'll take a look at admission controllers in some depth, more than just a surface scratch, and get some ideas about where we can really go with admission controllers if we had more than an hour or a day or a week to really dig into things, and then we'll wrap things up. So one of the things we're also going to be touching on, and I forgot to unhide the slide in between here, we're going to be using the Cloud Security Flight Simulator platform that we've built for Sec 540 and is going to start showing up in other courses and perhaps some workshops throughout the rest of this year. We're going to take a look at some of the features in there for Kubernetes as well. But before we do that, do a real quick overview. So big picture history. Kubernetes is about 10 years old as far as being visible in the outside open source world. Prior to that, it built on internal systems that Google had used to scale their computing massively, right? It's something Google designed and worked on. The assumption that it can scale up really big, I think, is a generally safe one if it's coming out of Google. Only hit, well, version 1.0 was shortly thereafter, about a year, and part of that 1.0 maturity and the momentum that Kubernetes came out of the gate with, I guess maybe led to or encouraged the forming of the Cloud Native Computing Foundation with Kubernetes as one of the core projects there. Key properties, it is a container orchestrator. So if you're used to running a Docker container to wrap a tool up into some nice reusable, portable, immutable spot that you can run it, Kubernetes is designed to run hundreds, thousands, tens of thousands of those containers in a coherent, managed way. And to have that configuration be declarative. So you don't go through and say, okay, change this, then change this, then change this. You say, I want one of these, make it happen. And Kubernetes deals with how to make that happen in the background without you having to worry a whole lot about that. If the things you want to make Kubernetes do aren't built in, it's immensely extensible. So you can create custom resource types. You could create a Kubernetes definition for a SANS courses range or a thermostat that you keep at a setting in your house. Immensely flexible, extensible, entirely up to you how you want to use that. And one thing that took me a while to really get the value of coming into Kubernetes, I'll say a bit late. It's been around for a decade, so the rich metadata is immensely powerful. And it wasn't until recently that I really grasped how massively important that is for Kubernetes and scale in general to work. And again, what it does, let's take a look at how it does it, what those pieces are. One of the core tenets for Kubernetes is that there is a strong separation between the control plane and the worker nodes. So all of the, what's our desired state lives in the control plane, and it's, okay, here's how we store it. We interact with the Kube API server to say, I want something to change. It gets persisted to a data store. Quite frequently, that's etcd. There's a scheduler and a controller that help decide where should this get put on which worker node, how do we get this brought into line, how do we get the various resource controllers to, say, make a pod and have that happen. And optionally, there's now a first-class cloud controller manager, so that can understand that the Kubernetes control plane is running in some cloud provider, and there's a nice structural, here's how to manage a cloud with flavors, if you will, for various known specific cloud providers. Separate from that, we have worker nodes. So they have a kubelet that talks to the API server, kube proxy for networking. And towards that extensibility, many of the core pieces of how to get some package of software in a container running are pluggable and interchangeable. The runtime, you can use runc, Docker, containerd. Like I'm forgetting one, but if you follow that container runtime spec, you can switch those out. You can switch out how you do storage and networking. And that has that nice distinct layer where you can say, I need a storage volume. And Kubernetes cluster says, aha, storage volume, I know how to do that. And I'm in AWS, so I'll do it this way, or I'm in Azure, so I'll do it this way, or I'm on a Raspberry Pi, so I'll do it this way. And a lot of words on the page, kind of patch pieces together here. Take a little bit of a look at this. So a laser pointer here, as an administrator, we talk to the API server. That is the front door for everything. If you're in a cloud provider, or if you're in a managed Kubernetes service offering, could be cloud provider, could be something entirely separate. You'll interact with the API server, but you won't have control over what's in this control plane box. That's your Kubernetes service provider's responsibility. In that shared responsibility model, many cloud providers have published. You can interact with it, but you don't get to see the insides, if you will. So we make a request, API server does its thing, checks with the controller, managers, the scheduler, persists it to etcd. It says, okay, this is part of our desired state now. Then the schedulers and controllers work with the kubelets on a worker node or many worker nodes to say, okay, we've got a request. This web pod service and ingress are now part of our desired state. How do we make that happen and connect those pieces together? So this container gets a network service, gets a connection to the outside world, and our users can now see our website.
We're just shifting some of that, how we need the data.
One thing that I
my window too.
don't like about this drawing, particularly, leads to tiny confusion, at least in my mind. The namespace does not live within a node. Namespaces span worker nodes. I'm more of a visual person, so I had a drawing made. Kind of take another view of Kubernetes that I hadn't seen anyone do this before, so I thought, what would this actually look like? So we can have multiple zones, so we can split our workloads, say between availability zones in AWS or between racks in your data center, and split the nodes out across those zones to get some resiliency. So if zone 2 goes away, we still have capacity in zone 1. And how Kubernetes sees those zones is through that metadata, through labels saying, this node is labeled zone equals 1, color equals charcoal, or color equals blue. And we can mix and match the node types too, right? Maybe we're starting to get into doing some AI workloads, and nodes C and D here might have GPUs or massive compute, and we can use those labels and say, okay, we want to run this, but run it on a node that has these properties, these labels defined, and spread the things out. And the namespaces we see these sort of long rectangles on the top, span across the nodes. Another thing to keep in mind as we start digging into this, the pods that are shown there contain, the pods may include more than one container. And the numbers aren't really, it's not really balanced, but we can apply those things. They group together, travel together, and share their life cycle, but it's not only one container in a pod. We have a pretty good idea here how things are structured, what they look like. So that's helpful. How do we declare one of these declarative configs? And if you're been around in the DevOps or cloud infrastructure world for a while, surprise, we have YAML. JSON is also supported. I have not often seen JSON Kubernetes manifests, but they are supported. Typically, it's YAML. There's 4 required-ish fields. The vast majority have API kind, metadata, and spec. The one, and we'll see this later, that fluctuates a little bit is spec, and the impression I get from where I've seen those is the reason it's not called spec is historical and just intractable to change at this point in time. So the API version and kind are key things. That tells us what type of controller is going to be used to control these resources. So we have a pod controller. Remember back in the diagram a couple slides ago, there was also a load balancer or a service that has a service controller as an ingress. That would be an ingress controller, and they're versioned. So a V2 pod may have a very different spec than a V1 pod. Who knows? When the V2 pod comes out, we'll learn more, I guess. I mentioned annotations. So labels let us select resources based on the labels. So we can query with the Kubernetes command line, show me all of the resources with the label environment and a value on that label of demo. And we get all of the stuff pulled together in one shot, which is great. Also can do things like when we define a service and say, power this service with pods that have the app label public web. That's great. So the labels let us search, find resources, make decisions, connect pieces together in really meaningful and cool ways. Annotations, on the other hand, we don't get to search, but we can put arbitrary, locally meaningful data in those annotations. And that can be immensely useful for investigation after the fact or for just carrying around data as we're doing inspections later. So in this case here, we said, okay, for dm.paper, so our fictional Dunder Mifflin paper company that we use for our mockups and modeling in Sec 540, says the data class is public. Great, data classification attached to the resource that's handling the data. Oh, would that be lovely? Where's all my private data? We'll just find all the resources that can hold data and check their annotations. Here we go, vulnerability rule. Now, CF90, okay, I made it up, so I know what it means, but right, it only has to be locally meaningful, but criticals with fixes have 90 days to be remediated. Like, you can compress that data in there, you can expand it so it would run off past the end of the slide. It's quite flexible. When we get to the specification is where the real depth and breadth of our configuration space lies. This one, we've got 3 top-level elements in the spec shown. I want to draw attention to one quick little thing here. This little dash in YAML, for those who are not blessed with the scars of having dealt with it for too long, means that's an array. So containers, plural, it's an array of 1 right now. We could have 2 more, 3 more, 50 more. I haven't run into a boundary on how many containers can put in yet. I don't expect I will. We'll give it a name and a source for where that image can come from. We also have init containers that are a little bit different lifecycle properties than the main containers, but are immensely useful. Here we can maybe infer that this container at init time runs some tool to fix permissions. Great. It's fairly tractable. There are a lot of defaults and optional things not shown. As I was looking at this, prepping for this and doing some other research, I decided to take a look at one of my new favorite Kubernetes commands, kubectl explain, which will take a resource type and start giving you an explanation of what all the properties are at a certain layer. And there's a recursive version, which will just give you one line per item. That recursive explanation of pod.spec is over 1,000 lines long. There are a lot of options for configuring a pod. And I'm not trying to pick on pods, but since that's where code executes, that's one of the core building blocks to make sure we understand. We're going to keep using pod as our target resource type today. But there's a massive configuration surface for a pod. And we'll get to it here shortly, how emission controllers can help us with that. So our quick takeaways on 15-minute intro to Kubernetes. It's flexible, large configuration space with largely consistent structures, which is helpful for us. Because there's so many defaults, so many optional things baked in, we're going to have to put some effort into securing this. That's just the way it is. Vendor defaults have not been safe ever. Fortunately for us, there's thriving ecosystem of tools available. We'll get to a couple of those today. And the rich metadata gives us a wonderful opportunity to search for things, to find based on data we can assign as we're building these resources. And we can then look up additional data down the road, which is an immensely powerful tool that can be easily sort of hand waved away as it's just metadata. Do yourself a favor and pause and dig in to think on what that should look like and ways you can make that useful to you. So, quick intro covered. Let's take a look in our cloud security flight simulator environments. So pop over to my next screen and close this. I don't like that little bar moving past there. So let's just make sure we got a good connection. And I'm going to refresh this. Okay, so in our cloud security flight simulator, we've got VS Code set up for accessible over the web. And I want to talk real quick about why we chose to do it this way rather than using GitLab's built-in VS Code IDE. Three main reasons. One, the idea of being able to set up a workspace where we can have multiple different Git repos checked out. We can have things that are not our Git repos out and handy, and we can have a view that's more than just one repo at a time. We felt very important to being able to work efficiently within the course content, and just professionally, that's more realistic as far as how we're going to do things. Another, here, hit Control backtick, and we have an embedded terminal that lets us access resources on the server without needing to go have yet another window open. And we can get this nice coherent view of all the pieces together. And see in my command history here, I just started up a Minikube cluster before the webcast started. Take do a real quick kube control. Version, and we've got server 128.3, client 128.0. So got that going there. The other thing that was a huge deciding factor for us was VS Code extensions. We've got a good number installed, and some of them don't really show up inside, but Docker, we can get a quick view of the images. What else is running? We can see that we've got several Docker containers running locally on our DevOps server. Got some Terraform tools, GitLab workflow that's available but not configured. And we've got a Kubernetes plugin, which, if you're new to Kubernetes, can be an excellent tool for helping find your way around the huge and complex resource space. So take a look here, namespaces, that's what we start with out of the gate. Go part of the demo will give something actually to look at here. So kube control, apply the configuration in the file called demo deployment. So that has created a namespace and a deployment. If we refresh our cluster, so we've got the demo namespace. We're going to use that one. And then we can start looking around. One thing I'm going to call out early, we have no custom resources set. This is a generic, fully upstream Kubernetes distribution. When you have a cloud provider or managed Kubernetes offering or something that's actually been configured a little bit further, you will have custom resources present. That is normal and good. It's not something to really be afraid of. Anyway, we've got one node. We can see some info about it. So we can click on it. We can get the definition. We can click the little I and get a describe. So this is the same as TL describe node minikube. And if you're haven't quite got the hang of the syntax or the other, or just prefer being able to click and move through, you can get access to that same info. And here I mentioned labels. This one minikube node already starts off with, what is that? Call it roughly a dozen labels and has some annotations on it about other things that are not necessarily desired to be searchable, but are available. If we go look at our workloads, we can see we've got pods, one for our Nginx deployment, and again, the little I shape to describe. Here we get our pod definition, which we started off, had just a few things. We get a bit more than an example in the slide. We've got Nginx, names, ports, resources, a lot of things available in here, and many of that were defaults. We can also jump into the logs, some real those, and we can even open a terminal inside the container running Kubernetes across, like, all from our web browser, which is very, very handy, very quick and accessible for these things. And one thing I noticed in our describe is that I need to fix the demo deployment. So I'm going to change this to latest. And we will just apply that configuration again, our declarative configuration. We'll make a change. We just apply it again. And you'll see there's multiple resources. The namespace did not change. Our new deployment has been configured. If we pop back to Kubernetes, give this a refresh, look at our pods, and we should see this image is running Nginx latest. It's already replaced the old pod with the new one faster than I can talk through and show how to get there. So that's our very quick intro to Kubernetes and the related tools in the DevOps server and cloud security flight simulator. All right, let's forge on and get into admission controllers. At a high level, there's small bits of code that run on requests. So I want to create a pod. So admission controllers will go through and either create, modify objects or decide if they should be admitted into the cluster or not. There's two phases. So mutation happens first and it's serial. Right? Say, I'd like a pod. Mission controller one in the mutation. So I'll say, oh, okay, I need to add a request limit to it. Next one, say, oh, I'm going to add these labels. Oh, I'm going to add an annotation. They go down the chain, the end. The validation ones will take that mutated request and get sent out to all of them in parallel. Say, okay, all of you validators can give me a thumbs up or thumbs down on this. If there's one thumbs down, then the request is not permitted to enter the cluster. There's about 30 built-in, enabled by default admission controllers. The set is, like the recommended set is part of the configuration from the upstream Kubernetes project. And the additional controls to enable or disable happens on the Kubernetes API server, which if you're running a managed Kubernetes service or using their managed offering, you likely do not have control to make changes there. So kind of beholden to your managed service provider for configuration of the mission controllers. Except if they've got the mutating and validating webhooks enabled, you can configure those to call out to anything you like, services in the cluster, URLs off cluster, and extend that mutation or validation capability to whatever you can dream of and code, or to whatever you've seen that other people have built and you find can be useful for you. So that flow, very basically, here's my pod spec. I'm going to say, okay, the API, am I authenticated? Yes. Mutating admission controller. Let me add some labels. Send it back. Add some annotation, send it back, right? To each different mutating webhook gets run in an order. So a late one may overwrite something that was created by an early one. The ordering will matter. Want to keep an eye out there, but it's serial, right? Everybody gets their chance to sort of edit this document before it goes out to be reviewed. There's a step that validates the object scheme. So at this point, I had a bunch of different mutating webhooks and mutating admission controllers that have said, I'm going to make my edits. This green step in this flow says, all right, I'm going to make sure the format, the structure of this request is still structurally valid. Not the contents of it, but it's structurally valid. It could be allowed into the cluster. Like if somebody, right, if one of these mutating webhooks corrupts the document, it'll get thrown out in this step. After it's been confirmed valid, all these mutations and edits have been done, it gets sent out to all the validating admission controllers, and they will inspect pieces of the document or the whole and say, this is good, this is good, this is good. This needs a warning, or this, we don't do this here. This is not allowed in this cluster, and reject it. If all the validating admission controllers pass, that request is persisted into etcd or whatever other cluster store is being used. And then the rest of the Kubernetes control loops pick up and say, hey, there's a new object in etcd. Let's make that happen. So the recommended set changes by Kubernetes version. And on the Minikube version that I've been using here for the demo, we can do a cluster info dump, and that will give us the API server's logs. You don't get that in a managed Kubernetes service because you don't get to see the API server very well. So it tells us it loaded 12 mutating controllers and 13 validating. The bolding I did, the blue text is the match for the grep. Just if you're wondering why those things look so weird. A couple of things I want to point out here. Limit ranger appears in both lists. It is both a mutating and a validating admission controller. It's kind of neat. You can be both. Limit ranger's job is to set default requests and limits for pods as they come through. Say, oh, you didn't say how much CPU or memory you want? I'll give you a default. In mutating mode. In validating mode, it says, hey, you requested 75 gigabytes of RAM and 64 CPUs? No, we don't allow that. That's too much. Request rejected. That focuses on the pod scope of resources. Another one, similarly, resource quota, is a validating, and it enforces quotas for a full namespace. So you could say, this namespace in total should use no more than half a CPU and 16 megabytes of memory. And then you've prevented that namespace from overwhelming cluster resources. You may also have prevented anything from running in that namespace, depending on what your workloads look like. That can be a good thing. As we go on and say those 25 that are enabled don't meet our needs, we can start going to dynamic admission controllers. We can write our own. We can install third-party ones, open source or commercial, and connect them in. Say, okay, I've got this really cool thing that I want to use to apply my policy to the cluster. I'm going to wire that up. And to do that, you use a validating or mutating webhook configuration. And here we see the API inversion. Rather than the pod, which had just the v1, this has a API/version. And here's one where webhooks instead of spec at this point in there might be one of those historical things that's hard to change. So what's our configuration look like? We're going to give this a name, and we're going to match namespaces. So we're selecting namespaces based on the labels applied to them. So if that namespace has a label called environment with a value of either prod or staging, then this webhook configuration is in scope. It's one we're going to consider as that request object comes through. Next consideration, some rules. What types of resources and actions does this apply to? We'll say, okay, if we have a list pod coming that matches this top part, well, that's going to get skipped. So we're not interested in that as a validating webhook here. Only interested in deployments, only interested when they're created or updated. We don't need to apply our policy when these are deleted, because when they're deleted, they're gone, and doesn't matter to us anymore. And then the client config gives us that flexibility of specifying how and where do we want to send this. In this case, it's a service, which implies it's something running in cluster. There's a service called validation webhook service in the namespace DM webhooks system. Okay, that's findable. Kubernetes DNS will be able to look that up, sort that out, and identify where that workload is. And then we'll send the request to this path on that service. And those pieces are configurable to us. We can put them to be what we want. Instead of a service, we can also define a URL. We can send the request to something off cluster and get an answer. One of the other properties in here that's important to keep an eye on, but isn't yet shown, is the timeout. We don't want our cluster sitting and waiting for an hour to make a decision. So there's a timeout to help protect against sort of being stuck because you haven't got answers back from your admission controllers. one of those third-party external admission control tools is Open Policy Agent's Gatekeeper project. Open Policy Agent, or OPA, is a toolkit for the CNCF designed to be able to write reusable bits of policy in a language called Rego, define it, and then you can use the toolkit to enforce it in different contexts, in different places, and different tooling that allows you to sort of write the policy once and enforce it in many places. It's a really great idea, right? I would love to be able to have, right, my policy engine, my policy rules are written the same whether my app is JavaScript or PHP or Python or Golang. Okay, here's how we make the decision about a business rule. In this case, for Gatekeeper, it's how we write our policy decisions for Kubernetes resources. And many of these can be used in command line before you commit these things to Git. So as Eric mentioned a couple weeks ago, having some of those early controls, shifting security left, say, okay, before I commit this to Git, my Rego, my open policy agent conf test runs and says, hey, we don't permit pods without resource quotas defined. And that Rego can pick that up. And it can also be very similar or same running in the cluster. Rego is a really, really powerful language. It is also has a steep learning curve, I've found. It's designed to be able to support nested data very, very deeply and very efficiently, and focus on the results rather than how to form a query. And that can make it a bit, made it a tough learning curve for me. It's taken a while to click, if you will. So we're going to jump into an example here from the OPA Gatekeeper library. And so mentioned, it took a while for me to get the policy ideas and how these fit together to click. The Gatekeeper team has published a nice library of policies and templates and constraints and examples, done an excellent job of making, here's some policies that people commonly want to do with configuration and documentation stuff available. So it's a great way to get started and get some configuration and some guardrails applied to your clusters as you're learning the language and trying to get to be more comfortable with it and explain things through. Colleagues of mine have also found that ChatGPT can do a fairly decent job of telling you what the policy does and describing it. But as with any of those things, your mileage may vary. So this particular policy package uses a violation framework. So if the code within these curly braces is true, then the violation will be true and the message will be passed back with the violation. So we write the policy to say these things are forbidden. And when that matches up, we get a violation. The violation gets passed to a gatekeeper, and it will decide, okay, this is a violation, but in this context, we're only going to warn. So it violates policy, which is what we're looking for in the code here. And that, right, we're looking for bad rather than good, which has its own trade-offs. At any rate, so here we go, find all the containers and consider each one as container. You set image to be the image property of any one of those containers. There may be one, there may be dozens. The Rego language kind of deals with that, so you don't have to decide, is this a for loop, is this a map reduce, how do I want to just say consider consider any container in our list, consider the image in that container, and if the image starts with any of the things in our input parameters bad repos list, then that's denied. So we can have here parameterized. So we can externally list our bad repos. And if any container image comes in for any request, it says, hey, this is a bad repo, it will get marked as a violation of policy. And then a separate configuration will decide, does that violation of policy mean warn? Is it just audit so we can count and get an idea what's going on? Or is it going to block the request? And the way the gatekeeper is set up with that, and I've seen this for other ones as well, you define that policy piece. And since it's parameterized, right here on the top, we've got a constraint template. It generates a new custom resource definition called K8S disallowed tags. And it has the package with the policy stuff all packed in there, not shown because it won't fit on the slide. But we'll take a look at it in just a moment as well. So we've got the policy. We have a list of tags that are not allowed. What is that list, you say? Doesn't matter. My policy is to take the object you've given me, the parameters you've given me, and test them against each other. So constraint template defines the policy in the generic. The constraint references that template. It says, hey, I need a disallowed tags policy applied to resources that match this spec.match object. So in this case, I want to apply a disallowed tags policy to resources that match pod in the namespaces default and demo. Okay, what parameters do we want to leave with that? Well, we're going to deny the tag called latest. We're going to deny the tag called test in our image specification in this instantiation of the policy. We can instantiate a different set of rules for a different namespace or for different resource type. We have that flexibility because the template and the constraint are separated. And one of the things as I was starting to learn Rego and piece together just enough policy to work and started looking at examples in like the Gatekeeper library, they've been through the scars of trying to write these policies and kind of realize, hey, you know what? Occasionally we need exemptions. So some of those pieces are built in already and kind of go, oh, okay. Yeah, we're gonna allow trusted / OpenEXP latest. That image is allowed to use the latest tag, nothing else is. So some of those community policy libraries may be a bit more mature than where we as individuals would start off, and nothing else is a great resource to take a look at and get some inspiration for how you want to do things, or say, you know what, this meets my current needs, I'll run with it. So let's take a look at that. Clear my screen here, maybe make the font a little bigger. So if you'll bear with me here, we're going to install Gatekeeper on our Minikube cluster. I'll get a drink of water while this is happening. Okay, that didn't take long at all. So getting this set up, very quick, very easy. There we are, we're off and running. Gatekeeper's installed, create a bunch of things. Let's take a look at our Kubernetes view and see what kind of things it created. Well, to start off, we now have a bunch of custom resources. We've got constraint templates. We've got configs, we've got some providers. A bunch of custom resources came in from Gatekeeper. So we don't have any constraint templates defined, but we have the resource type defined. All right, that's pretty cool. We'll also take a look at, so we've got a new namespace called Gatekeeper System. Control, let's just get all resources in the namespace, Gatekeeper System. Kube control, if you set it up well, will do tab auto completion to save you loads of typing it's worth your time to do that. And here we will see we have a service called Gatekeeper Webhook Service. Well, that's probably connected to validating and mutating webhook configs. We've got an audit deployment and a controller manager deployment. Those each have replica sets associated with them, and those replica sets have pods powering them. So here we see the audit just has one pod, but the controller has got 3, so there's some resilience. If you need to make a decision, you need to have that policy checked as things are coming in. You want to make sure any one pod going away doesn't impact your cluster that way. So that gets us cluster with OPA Gatekeeper installed. And we can now get that configured. So this is from the OPA Gatekeeper library. It's the disallowed tags policy. And right on their website, you can see, right, we've got description, that's an annotation. We get lots of nice documentation in there. We're defining a new custom resource type. We've got a schema in Open API v3 to validate that parameters coming in are the right shapes. We've got our Rego policy, much more rich than what I had shown on screen, but it gives you a very clear idea. We can start doing more and more with this, and even imports a library called exempt container, and the function is exempt, which, right, we've got libraries, we've got usable things. There are many policies where a container image might be exempt from the policy. So standing on the shoulders of the community, right? No, have a library, we can just say, hey, I know how to check container for an exemption. That's wrapped up. It's a nice little reusable component. We can run with that. How to apply? You can apply it straight from GitHub. Your risk profile to decide if that's the way you want to go. And here we have an example constraint. So we apply this to pods in the default namespace. We're not going to allow latest, except for these images. And then they've got test cases for all of various different variations, no tag, single disallowed tag. Lots of great documentation for use cases to think through, commands to do the testing yourself. Wonderful, wonderful resource. So let's get this installed. We'll create our template. kubectl, apply the file, called gatekeeper-template. Right, so there, create a constraint template. Quick, go back to Kubernetes and take a look at our custom resources. Do that little refresh, and we now have a constraint template called Gates disallowed tags. We also have a new custom resource called Gates disallowed tags. There's our template. It's now a Kubernetes object that we can apply to different places. So we'll look at our constraint here and say, hey, we've got our trusted busybox image. We're going to disallow latest, current, and head. All right, so let's get this applied. We'll go for gatekeeper constraint, and this is applied. Just real quick for grins, we'll refresh our Kubernetes view and see we've got this disallowed tags exists in the cluster, and here's an annotation. Kubernetes applied the last applied configuration is an annotation. Almost gives you an idea for a rollback capability there. And it's got a status object. Let me focus in a bit more on this. Okay, so we've got it's enforced, we've got status by pod. Okay, so there's some good stuff in there. Let's take another look at this with the kube controls CLI. Control get constraints. There we go. Okay. All right, so we've got a constraint. And when we look at the summary, it gives us a total number of violations. We haven't had anything new come into the cluster. We didn't launch a new deployment, but we have a policy violation detected. That audit pod has gone around and said, hey, I've got a new policy. Let me explore the cluster and see what resources are violating the policy. That's the URL if you want to join on Discord later if you've got questions. So let's describe our disallow tags. Audit timestamp. Total violations 1 in here. And we get a nice message out of this. Container Nginx uses a disallowed tag, Nginx latest. Disallowed tags are latest, current, and head. So our Nginx deployment is in violation of policy. So we can fix that real quick. Nginx latest, we'll go to 1.25.0. Save that and redeploy Nginx. Change our deployment. That's reconfigured. And we can see this pod restarted 9 seconds ago, which means it passed through that validating admission controller and was allowed into the cluster and allowed to run. So the next time that audit cycle goes around, that policy violation will get cleared up. But in the interest of time, we're not going to wait around for that. We're going to start looking forward at some other things here. So you're getting an early grasp, right? You can have it in audit mode. You can find your policy violations if you're not ready to start breaking things, which is a great way to introduce security controls to your pipelines. Can do warnings and messages and give some good feedback to your developers. As we go forward, one thing we didn't have time to really dig into today, OPA Gatekeeper, as well as many of the other open source and commercial admission controller suites like Caverna or KubeArmor, they support querying external data. So where would we want to go with this? We could query our image repository, our image registry, and say, hey, I'm about to run this image. Are there any critical vulnerabilities? And make a decision based on that. You could call a chaos engineering failure injection service and say, hey, what do you think about this? And it might just say, hey, you know what? Your 100th request denied, and start injecting faults to do resilience testing. Up to you how much you want to explore that early. That may be a later down the road maturity thing, but there's some really fun things you can do with that. If you're interested in like supply chain security, making sure you've got signed images and software bill of materials, you can go query those things. If you're interested in that as well, come back and join us in a couple of weeks. John Ziola is going to be giving a similar webcast digging into those challenges in the technology space as well. A couple others, you can constrain the namespace names. So you maybe don't want to have a namespace called com or edu. You could go check config maps for secrets because Kubernetes has a secrets object that's designed for storing them, and we probably don't want them in our config maps. Lots and lots of ideas you can do with external data. So sky's your limit there. One other thing that I'm really excited about, Rego is immensely powerful and awesome. It can also be challenged to learn. and having to bring in, regardless of how quick it was to install, bringing in a third-party piece to do some simple validations, it feels a bit heavy. So Kubernetes has got a validating admission policy controller. It's still in beta. It only works in the validation phase of admission control. But it's coming built in as part of the Kubernetes base. And it's, as of 128, it's a beta feature. You will see it listed if you look back at the slides in the enabled admission controllers, but it's blocked by a feature gate, which your Kube API administrator, so if you're a managed service, Kubernetes service, their responsibility to decide when it's ready. But it uses a different language than Rego. It uses common expression language, which I have found much more approachable for very straightforward things, and is designed to have a syntax closer to like a C or JavaScript or Golang. So we can say, hey, in the object specification, replicas should be less than or equal to 7. Nice, clear, straightforward and easy. We can put in parameters of, say, hey, we'll get our parameters from a config map. We'll fail when this is invalid, and we've got this expression, and we can have multiple expressions in the validation in there. So really exciting built-in capability sort of coming down the line. And again, follows similar pattern to how Gatekeeper has. We define a policy, and we say, here's where to get the parameters. And then we have a binding that says, hey, I want to bind this policy to resources that match this. So here again, we're matching based on labels, using that metadata to decide where should the policy be applied, which is great control and precision around that, and also requires us to populate that metadata meaningfully. And then we'll get our parameters from a config map that's in a specific namespace. And we've got our data in there using that native Kubernetes objects to bring your configuration in. And now you've got these policies that can be in code, they're declarative and designed to execute very quickly. And again, we can define here what action do we want to take? Do we want to deny the policy? Do we just want to audit? We want to give a warning feedback? Our choice. We don't have to turn policy on and have it be, no, the gates are shut, the gates are open. Say the gates are open, but we got somebody there with a counter, making sure we know exactly who goes in and out, and we can start dialing those in and strengthening them over time. And there's libraries of those policies, right? The wisdom of the community, the efforts of the community are being shared back out to say, hey, here's some common policies, let's share them on GitHub and have that out there. So wrapping it up, Kubernetes is a complex beast, no doubt about it. Immensely powerful and a lot of tools that will give us the ability to run things smoothly and cleanly, and admission controllers are a critical part of that. Gives us essential capabilities to making sure our clusters are secure, performant, and as time marches on, we're getting more and more capability brought into the Kubernetes core, in addition to a thriving ecosystem around it that will let us expand beyond what was sort of what came in the box. We can start bringing out many more things, bring much more capability to bear, and have fun playing and learning as we go as well. So with that, we're going to wrap up here. For questions, I'm going to hop over to Discord here after a couple minutes after this webinar, and I'd be happy to take questions in the workshop discussion channel. And with that, I think we're at time. So thank you, everybody. Have a great remainder of your day, and join us next time. Join us on February 1st for safeguarding the software supply chain. Thank you very much.